Hello students, it's Kailash. In Electrostatics lesson of 12th standard, under Coulomb's law section, you will come across two excellent quantities, beautiful quantities. Permittivity of a medium denoted by the symbol epsilon and relative permittivity of a medium denoted by the same symbol epsilon with a subscript carrying the letter R. So epsilon sub R. So in this video session, I'll try to make you familiar with these two quantities. Okay. Now, before going into the definitions of these two quantities, we shall firstly see what is electric field. You know, you always have an influence region around a magnet. You term it as magnetic field. Likewise, around a charge, you will always have an influenced region. So that influenced region, what you find around a charge is called electric field. So if it's the influence region around magnetic field, I call it as, if it is influence region around a magnet, I'm going to call it as magnetic field. And if it is the influence region around charge, I'm going to call it as electric field. So the space or region around a charge where its influence is felt is called electric field. Electric field is an invisible entity. So to visualize electric field, we usually represent it in the form of either straight lines or curved lines, depending upon the nature of the charge or system of charges. Now, those lines, what we use to represent electric field or what we use to picturize electric field are termed as electric field lines. I will be discussing electric field lines in detail in my subsequent videos. So just be familiar with this term electric field line. So electric field is picturized or visualized in the form of electric field lines. Now let me consider an isolated positive charge plus Q charge. If I try to draw electric field lines, if I try to represent the electric field around this charge in the form of electric field lines, it will be straight lines directed outwards. Now let me consider a negative charge, an isolated minus Q charge. If I attempt to draw electric field lines around a minus Q charge, a negative charge, it will be again straight lines, but with one difference. It will be directed inwards. So if it is isolated positive charge, the electric field lines are straight lines directed outwards. And if it is an isolated negative charge, then the electric field lines are again straight lines directed inwards. Now, if I place these two charges in air medium, then the electric field lines surrounding these two charges should pass through air medium, for which air has to offer permission. If I place these two charges in water medium, then the electric field lines has to pass through water medium, for which water has to offer permission. So the permission what a medium offers for the passage of electric field lines has got something to do with permittivity of the medium. So based on this, we shall try to define permittivity of a medium. So permittivity of a medium is the conducting power or ability of a medium to conduct electric field lines, or permittivity of a medium is the allowance or permission offered by a medium for the passage of electric field or electric field lines. If electric field lines finds it easier to pass through a medium, then its permittivity is high. If the electric field lines really finds it a tough time to pass through a medium, then the medium's permittivity is smaller. So permittivity is the allowance or permission offered by a medium for the passage of electric field lines. And permittivity has got only magnitude and has got no direction. Therefore, it is a scalar quantity. And its unit is Coulomb square, Newton to the power minus 1, meter to the power minus 2. So please make note of the unit of permittivity. Now, permittivity of air or vacuum. So you should know one thing about permittivity of air or vacuum. See, whatever value you assume for a quantity in vacuum is otherwise called free space, the same value we assign it in air. For instance, the velocity of light or speed of light is 3 into 10 to the power 8 meter per second. So this is through vacuum. And the same value we assume it in air also. So the velocity of light is also taken as 3 into 10 to the power 8 meter per second in air. So whatever value we assign for a quantity in vacuum, that can be considered in air. Okay. Now, what can you say about permittivity epsilon naught of vacuum or air? Permittivity denoted by the symbol epsilon. If it is vacuum or air, I have to use a subscript O. So epsilon O. Now, whenever I want to compare permittivities of two media, one of the media should be air. That is to say, the permittivity of air or vacuum is always taken as a standard. If I want to compare permittivity of water, I have to use air as a standard. So I have to compare permittivity of a given medium with permittivity of air or vacuum. So permittivity of vacuum or air is always taken as standard while comparing permittivities of media, and the denotation for permittivity of vacuum or air is epsilon sub O. The value of permittivity of vacuum or air, free space or air, is 8.854 into 10 to the power minus 12 coulomb square, Newton to the power minus 1, meter to the power minus 2. So make a note of the value of permittivity of air or vacuum. Now, the result, what we get on comparison of permittivity of a given medium with a standard, that is nothing but permittivity of air or vacuum, will give us a term which we call it as relative permittivity. See, whenever you want to compare two quantities, mathematically, we have to find the ratio of those two quantities. If I want to compare A and B, I have to find ratio of A and B. So A divided by B or B divided by A. Okay. So whenever I compare permittivity of one medium with the permittivity of standard, that is air or vacuum, then the result what I get is called relative permittivity. Just be familiar with the word, with the term relative permittivity at present. Okay. Right. Now, we will go into definition of relative permittivity denoted by epsilon sub r of a medium. We'll have two definitions. We'll see the first definition. Relative permittivity of a medium is defined as the ratio of permittivity of a given medium to the permittivity of air or vacuum. You know, vacuum is otherwise called free space. So if I want to find relative permittivity of a given medium, I have to compare it with the permittivity of standard, that is nothing but air or vacuum. So it is the ratio of permittivity of a given medium to the permittivity of air or vacuum. It has no unit, it's just a number. Now, why is that? Now, based on the definition, I have written the formula for relative permittivity. So relative permittivity epsilon sub r of a medium is defined as the ratio of. So ratio means it's a division, right? So numerator contains permittivity of the given medium, that is epsilon. So whichever medium's relative permittivity you're going to find, that should come in the numerator. And the denominator should contain the permittivity of the standard, that is nothing but air or vacuum. So permittivity of air or vacuum, so epsilon naught. If you look at both numerator and denominator, they contain the same quantity permittivity. So numerator will have the unit coulomb square, Newton to the power minus 1, meter to the power minus 2, and we'll place the unit, again, coulomb square, Newton to the power minus 1, meter to the power minus 2 in the denominator. So since both numerator and denominator are similar terms or similar quantities, same quantities, their respective units will cancel each other, and hence relative permittivity has no unit. It's just a number. Right. Now, from this formula, I can write epsilon sub r is equal to epsilon divided by epsilon naught, where epsilon r is relative permittivity of given medium. Epsilon is permittivity of that given medium. Epsilon naught is permittivity of standard, that is air or vacuum. Now, cross multiplying this, I end up with epsilon is equal to epsilon naught into epsilon r. So this is very important. Don't forget this. That is, permittivity of any medium can be written as product of permittivity of the medium taken as standard, that is air or vacuum, and relative permittivity of that medium. So the product of relative permittivity of a medium and permittivity of air or vacuum will give its permittivity. Okay, so don't forget this product, okay, this relation in fact. Now, we will try to find value of relative permittivity of air or vacuum and the other media. You know, Relative permittivity is given by this formula. Already we saw it in the earlier slide. So permittivity of the given medium divided by permittivity of air or vacuum. Now, if I want to find relative permittivity of mica, then the numerator will be permittivity of mica divided by permittivity of air or vacuum. If I want to find relative permittivity of water, then the numerator should be permittivity of water divided by permittivity of air or vacuum. If I want to find relative permittivity of air or vacuum, then the numerator has to be permittivity of air or vacuum by the denominator permittivity of standard, that is again air or vacuum. So both numerator and denominator are same, so they cancel each other, and hence I will get 1. So relative permittivity of air or vacuum is 1. So the relative permittivity of air or vacuum is 1, and for all the other media, the relative permittivity epsilon r will be greater than 1. This is because permittivity of any medium will always be greater than permittivity of air or vacuum. So air or vacuum will have the smallest value of permittivity. Okay, so since epsilon is greater than epsilon naught, the value of epsilon r for all the other media will be greater than 1. So thus, for air or vacuum, epsilon r is 1, and for all the other media, epsilon r is greater than 1 because epsilon tends to be greater than epsilon naught. Now, relative permittivity has got one more name. It can also be called as dielectric constant. So please make a note of it. So relative permittivity is otherwise called dielectric constant. So I hope you would have understood the first definition. Okay. Now we'll go into one more definition for relative permittivity. So this is in terms of Coulomb's law. You know, force between two charges in air or vacuum, F sub V, is given by 1 by 4 pi epsilon naught into Q1, Q2 by R square, where Q1 and Q2 are magnitudes of the two charges, and R is the distance between the two charges, and 1 by 4 pi epsilon naught is a constant of proportionality, which appears in Coulomb's law. Now, if I place the two charges in air or vacuum, then the constant will contain permittivity of air or vacuum. Suppose if I place these two charges at the same distance in any other medium, then the same formula becomes force between two charges in a medium is given by 1 by 4 pi into, you have to replace epsilon naught by permittivity of the medium in which the two charges are located. If I place it in water, inside water, then epsilon naught should be replaced by permittivity of water. If I place it inside mica or inside oil, in fact, then the permittivity of air or vacuum in this formula should be replaced by epsilon, that is permittivity of oil. Okay, so F sub m is given by 1 by 4 pi epsilon into Q1, Q2 over R square. Now we know epsilon can be written as product of epsilon naught and epsilon r. Already we have seen it on the earlier slide. Therefore, I can rewrite this formula as F sub m is equal to 1 by 4 pi epsilon naught into epsilon r into Q1, Q2 over R square, because epsilon is equal to epsilon naught into epsilon r. That's why I have replaced the term epsilon by epsilon naught into epsilon r. Okay. Now what I'm going to do is I'm going to divide force between two charges in vacuum, that is F sub V, by force between two charges in medium. We are seeing one more definition for relative permittivity. Okay. So F sub V divided by F sub m will give me, I have the expression for F sub V in the numerator divided by, I have the expression for the same force between two charges in a medium, the denominator. Now cancelling the similar terms, 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught cancels off, and Q1, Q2 by R square, Q1, Q2 by R square gets cancelled off. Thus, all the terms in the numerator have got cancelled, so I'm left out with 1, and accepting 1 over epsilon r. So all the other terms are cancelled off. Therefore, I end up with 1 by epsilon r in the denominator. So 1 divided by 1 by epsilon r. This can also be written as 1 into epsilon r by 1, which means epsilon r will go to the numerator, isn't it? So the term epsilon r will go to the numerator. Thus, I end up with F sub V divided by F sub m is equal to epsilon r. So based on this formula, we can write one more definition for relative permittivity or dielectric constant. We shall see it in the next slide. So FV divided by FM is equal to epsilon R. So relative permittivity is defined as, we have division in the formula. So we should start our definition with ratio of. Now write the numerator first and then denominator second in the definition. Write about the numerator first and the denominator next. Okay. So it's the ratio of force between two charges in vacuum to the force between the two charges in the medium placed at the same distance. So whatever distance you maintain between the two charges in air or vacuum, the same distance you have to maintain in the medium. So thus my definition is, relative permittivity of a medium is defined as the ratio of force between two charges in vacuum placed at a certain distance to the force between those two charges in the given medium placed at the same distance. So this is one more definition for relative permittivity or dielectric constant. I hope you would have understood the definitions of permittivity and relative permittivity. So thank you then. Have a nice day further. So meet you in the next video session. Until then, it's Kailash signing off. Bye.